In this video, I'm going to do an example of a thin film problem. I tried to pick one of the harder ones. I'm going to operate under the assumption that you've mastered the Khan Academy video that we watched in class about thin films. If that's not true, maybe go back or raise your hand and ask me to try to explain it again. Just pause this wherever you get stuck and I will come over and help you. So this example, it says, a thin soap layer on water produces an enhanced reflection through constructive interference. So as soon as I see constructive interference, I start thinking about that idea that the change in length is going to be some integer of wavelengths. At a wavelength of 600 nanometers, when light is normally incident from air. So when I'm in the air, I have a wavelength of 600 nanometers. Oh, this stylus is not happy tonight. The refractive indices of soap and glass are 1.4 and 1.52. The second smallest thickness of the soap layer is closest. So I want the second smallest, so I want m equals 2. And now I'm going to see what happens. So when I look at this, the first thing I'm going to figure out is what is the wavelength if it's 600 nanometers in air, what is it in the soap? So since I know from last unit from earlier when we did refraction, that the index of refraction is C over V, I know, okay, well, if I'm in soap that's 1.4, that means the speed of light has gone down by 1.4 as well. Now, I also know about waves that velocity is frequency times wavelength. Now, frequency will not change, but the wavelength will. So since the speed went down by 1.4, the wavelength has to also go down by 1.4. So I'm going to do 600 divided by 1.4. I know that the wavelength of light in soap is 428.6 nanometers. In soap, it's 428.6 nanometers. Okay, and I want constructive interference. So that means that when it comes down and back, I want it to be in multiple of a wavelength, but I have to wait and check, did it flip? So when I go from air to soap, I'm going to something slow. I'm going to shift by a phase. The thing I think is what was constructive will now be destructive. What was destructive will now be constructive. But when I reflect from the soap to the glass, there's a second phase shift. So I'm going to flip my results and then flip them back. So since these are in order, I can keep my rule that the change in length is the integer, which is going to be 2 times the wavelength that it is in the soap, because the path length difference is into the soap and back out of the soap. So my change in length is twice the thickness of the soap. Since I want the second smallest, 2 times the wavelength, and I want to do the wavelength in that new material. So first thing I see, the 2's cancel. So the thickness that I want is just going to be the wavelength of that material, which in this case is 428.6 nanometers. Sorry, bad units writing with this stylus. What if it had gone from air to soap back to the air? Then I would want to look at that change in length is m plus 1/2. And I'd want to think that one through about what would be the smallest thing I could get, because then it would only flip, my rules would only flip once. I hope this is making thin film interference make a little bit more sense.